Hello everyone. Today we are looking at question number 39 from the GATE 2025 physics paper. This is a 2-mark question that beautifully combines concepts from nuclear physics and classical mechanics. So it asks us to predict the scattering direction of two projectile protons based on a specific nuclear interaction potential involving spin orbit coupling. This problem tests your ability to translate a mathematical potential into physical trajectories. Let's break the setup first. We have two projectile protons, P1 and P2, both with spin up along the positive z direction. Okay, and they are scattered one at a time by a fixed target proton T, which is also spin up. The interaction potential is given by V equal to lambda times vector L dot vector S. So this is the interaction potential and it is specified as negative. Our goal here is to determine whether P1 and P2 are scattered upward, that is towards plus y, or downward, that is minus y, based on whether this potential is attractive or repulsive for each particular case. So let us first establish the rules for the interaction. We are given that lambda is negative. So lambda is negative. This is what has been given in the problem. And since both the projectile and target are spin up, the total spin vector S points in the positive z direction, that is out of the plane. So we have S points in plus z. Okay. Now the sign of the potential V tells us the nature of the force. So if V turns out to be positive, the potential is repulsive, pushing the particle away from the target. So if V is positive, it is the repulsive interaction, and if V turns out to be negative, the potential is attractive, that means pulling the particles towards the target. So if V is negative, it would be an attractive interaction. So our entire task reduces to finding the sign of the dot product L dot S for each particle. So first let's analyze projectile P1. So it travels above the target, so it has a positive y coordinate, as we can see in the diagram as well. The orbital angular momentum L is simply r cross p, so it is r cross p, and using the right hand rule, point your fingers from the origin up towards P1, that is positive y direction, and curl them towards the momentum, that is positive x. So it would be j hat times I hat, so it would be minus k hat. So your thumb points into the screen if you just follow the right hand rule, which is the negative z. So L is negative. Okay. Now for the potential. So L is negative, or S was positive, so it turns out to be negative. So the dot product is negative because L is down, that is minus z, and S is up, which is plus z, so resultant is negative. Now substituting this into the potential formula, V equals lambda, which is negative, times this negative dot product. So V1 is lambda, which was negative as given in the problem, times L dot S, which is again negative as we just saw above, which turns out to be positive. So two negatives make a positive. A positive potential means the force is repulsive. So it is a repulsive force and it deflects to plus y. This is important. Now let's analyze projectile P2, same as we just did for P1. It travels below the target, so it has a negative y component, if you can see in the diagram as well. And let us check the right hand rule again. R points down, that is minus y, and P points right, that is plus x. So minus j hat times plus I hat, which is equal to positive k hat. So the term j times I is minus k, but we have a minus sign from the position, so the resultant is positive k. Okay, so L points out of the screen in the positive z direction. Okay, now for the potential. So let us write vector L dot S, which is positive as we just saw, and S is also positive, so resultant is positive again. So here L is up plus Z and S is up, which is also plus Z. They are parallel, so the dot product is positive. Alright, now substituting this into the formula for potentials, V equals lambda, which is negative times a positive number, L dot S, gives us negative. So V2 is negative. So a negative potential means the force is attractive, as we saw in the couple of slides earlier. Attractive. So since P2 is below the axis, an attractive force pulls it towards the center. So that is deflects to positive y. Crucial. So P2 also deflects into the positive y direction. So this is crucial to understand. So putting it all together, projectile P1 experiences a repulsive force and goes up. Look at here, both are in the plus y direction, and projectile P2 experiences an attractive force and is pulled up, but the forces were repulsive and attractive, and that gave us the both being scattered along the positive y direction. So this means both protons are scattered in the positive y direction. This creates a left-right asymmetry in the scattering, which is a signature of spin-dependent forces. Checking the options, this corresponds to option B. And before we finish, here is the physics takeaway. Notice how both particles scatter to the same direction, positive y. This is a signature of the spin-orbit interaction. If the potential were purely central, that is depending only on distance r, the scattering would be symmetric, some up, some down. But the vector L dot vector S term breaks that particular symmetry, and this effect is exactly what nuclear physicists use to create a polarized particle beams. By scattering unpolarized particle of a target, the ones that come out at a particular specific angle all have the same spin orientation. Okay, for a deeper dive into nuclear forces and two nuclear problems, I highly recommend the nuclear physics course by Professor H.C. Verma from Department of Physics at IIT Kanpur. I wish you all good luck for your preparations, and I'll see you in the next solution. Thank you.